Welcome back to our trigonometry series. Today we are up to section 2.1 where we'll be looking at the graph of sine and cosine. This is a continuation of our review of trigonometric ratios, cosine, sine, and tangent. These ratios compare the various sides of the triangle. The next step was to take this triangle idea and apply it to the xy axis. Here the same rules apply, where we have x and y and the r for radius. In a previous video, we showed that as you increase theta around the circle, you eventually got back to where you started from. So cosine and sine would rotate through some numbers, but end up right back where they started. This would happen every 360 degrees, or 2 pi radians. So what would it look like if we graphed these? Well, it would look like this. If you look at the sine graph, it starts at 0 when theta is 0. When theta is 90, it goes up to 1. When theta is 180, it comes back to 0. When theta is 270, it's negative 1. When theta gets back to 360, it's back to 0, right where it started. If you look at cosine, it's the same shape, but it's shifted slightly along the x-axis. In this graph, we have a data point every 90 degrees, or pi over 2 radians. How would it look if we took more data points between 0 and 360? In this case, we're taking a data point every 45 degrees. And here are the values for sine for all of those values of theta. This 0.707 is an approximation. There are many numbers that go after the decimal point. So what would these data points look like if we graph them? Well, it looks like this. The 0, 90, 180, 270, and 360 points are the same, but now we've got points in between them, creating a more defined shape. We can do the same with cosine and get its values for theta. This is how sine and cosine would look with these points. You can see here, at 45 degrees, sine and cosine are equal to each other. And if you think about it, a 45-45 90-degree triangle would have cosine and sine be the same, because the two sides of the triangle that are not the hypotenuse are the same length. So the ratio of those sides to the hypotenuse would be the same. So you can probably guess where this is going next. We want to take a data point at every degree of theta. What would that look like? Well, sine would start at 0 and slowly get larger. Cosine would start at 1 and slowly get smaller. This is what all those data points would look like. This is what a true sine wave looks like. This shape and these functions show up all over the place. You'll see them in engineering, mathematics, and even in nature and music. As we saw before, it takes the sine wave 360 degrees, or 2 pi radians, to get back to where it started. We call this the period. This is how long it takes for the function to begin its repeated cycle again. So like we've said a number of times, in this case it's 360 degrees or 2 pi radians. And the same is true for cosine on this graph. It starts up at 1, goes down past 0, hits negative 1, comes back up through 0, and starts up again at 1. So the period of this cosine function is also 360 degrees or 2 pi radians. In this case, because these sine and cosine functions repeat themselves every 2 pi radians, we can say that the sine of theta plus 2 pi, or any multiple of 2 pi, is equal to sine of that theta. The same is true for cosine. Cosine of theta plus 2 pi would just be equal to cosine of theta. This is because you end up at the same value of cosine or sine every 2 pi radians on the graph. So here's an example. Sine of 13 pi over 6. Well, that looks a little weird. But let's think about it as sine of pi over 6 plus 2 pi, or 12 pi over 6. We know when we have this 2 pi in here, we can just kind of pretend it's not there and end up with the sine of pi over 6. This might be a good time to refresh yourselves about what the various radian degree measurements are around the circle. So here, pi over 6 is equal to 30 degrees. And you can use a calculator or a chart to find that the sine of 30 degrees is 0.5. Looking at sine and cosine, we can clearly see they do not follow the same path. They are separated by 90 degrees on this graph. Some textbooks might call this a phase shift or angle shift. But this relationship is constant between sine and cosine. It doesn't matter where on the graph you look, there will always be a 90-degree difference between the two graphs. So we can say that the sine of any value, x, is equal to cosine of 90 degrees minus that value. Likewise, cosine of x would always be equal to the sine of 90 degrees minus x. So let's do a quick example. Sine and cosine of 27 degrees. Well, we can use Mr. Calculator to find out the values of those trigonometric functions. But because we have this 90 degree shift between the two graphs, we can also say that the sine of 27 degrees will be equal to the cosine of 90 minus that value, 90 minus 27, which is 63, which is approximately 0.454. So yep, that makes sense. It works. And we'll do the same thing with cosine. The cosine of 27 is equal to the sine of 90 minus 27, which again is 63, which is approximately 0.891, and we have a match again. This relationship between sine and cosine tells us that they are cofunctions of each other. In fact, all the trigonometric functions have a cofunction. Sine and cosine are cofunctions of each other. Tangent and cotangent are cofunctions of each other. And secant and cosecant are cofunctions of each other. As you can see, each trigonometric function has a 90 minus x relationship with its cofunction. If you need a reminder on these reciprocal functions, you can go back to section 1.4 where we cover cotangent, secant, and cosecant. Next, let's look at this basic 30, 60, 90 triangle. The 30 and 60 are complementary. That means that they add up to 90 degrees, which makes sense for it being a right triangle. The two other angles will always add up to 90 degrees, therefore they will always be complementary. So we can say the value of any trigonometric function of an acute angle, that being one of less than 90 degrees, is equal to the value of the cofunction of its complement. Now that seems like a lot of word salad, but it's basically putting into words the things on the left side of the screen. So for example, let's look at the first one. Sine of x, that is the value of that trigonometric function, is equal to the value of the cofunction, cosine, of its complement, 90 minus x, would be the complement of that angle. Let's jump over to the whiteboard and do some examples. All right, so up here, I'm just going to write the sine of 47 degrees. We want to express this in terms of its cofunction. So the cofunction of sine is cosine. So we can say that this is equal to the cosine of 90 minus the number we started with, 47 degrees. So 90 minus 47 is 43. So this would be cosine 43 degrees. So we took this function and expressed it in terms of its cofunction. These are equal to each other. Let's just do one more like that, and we'll do a different one. We'll do cotangent of 78 degrees. So what is its cofunction? The cofunction of cotangent is tangent. So this is equal to the tangent of 90 degrees minus the number we started with, 78 degrees. So this would be equal to the tangent of 12 degrees. 90 minus 78 is 12. So tangent of 12 is equal to cotangent of 78. Next, we're going to write down, I'm going to squeeze over a little bit here, the sine of 134 degrees. So we're just going to use a calculator. If we punch that out, we get approximately 0.7193. The question is, what is the sine of 494 degrees? Well, we've got a pretty big number here. And we know that the sine values repeat every 360 degrees. So we can take away 360 degrees, but we can write it like this. We know that the sine of 494 is equal to that number minus 360 degrees. And if it was even bigger, say like 800, we could take out 360 and then another 360 until we got to a number that was below 360. So we end up with the sine of, I'll just put in parentheses for fun, 134 degrees. Well, that's where we started with. So we just know that these are going to be equal to each other. And I can probably just make a squiggly approximate, 7, 1, oh boy, 9, 3. It's the same number we started with. All right, let's do one more here. And we're going to calculate the sine of 5 pi. There's a couple ways we can go about this, but using this example above, we can do something similar. We can say that the sine of the thing we started with, 5 pi, minus 2 pi. Right? We're just taking out a full circle's worth of revolutions here. We end up with 3 pi, the sine of 3 pi. And we'll write that down here, the sine of 3 pi. Well, we can still take 2 pi out of there. So this is going to be using this same equation. I'm going to skip a step and just say this is the sine of pi. Now, this is equal to 0, but if you haven't had that memorized, you could always just kind of draw yourself a circle. Right? Here's our x, here's our y. And starting here, if we draw pi over to here, or 180, what is our y value? Right here, we are at negative 1, 0. Our x is negative 1, and our y is 0. We're talking about sine, which cares about y. So the y value here is 0. That's it for today. We'll see you next time.